Okay, so we have seen how we can generalize trigonometric functions to allow for complex variables. So in this lecture, we will see how in a similar analogous manner we can use the generalized idea of the exponential function to also define hyperbolic functions. We'll also look at some of their properties. Okay, so we define hyperbolic cosine function of a complex number z as e to the z plus e to the minus z divided by 2, and the hyperbolic sine function of a complex number z as another complex number which is defined as e to the z minus e to the minus z the whole thing divided by 2. Right? So they are both linear combinations of the functions e to the z and e to the minus z. Both of these functions e to the z and e to the minus z are analytic everywhere in the finite complex plane, so they're entire functions. So a linear combination of an entire function is also entire. So immediately we see that the hyperbolic cosine function and the hyperbolic sine function, both of these are also entire functions. So the derivatives are also readily written down. So derivative of e to the z is just e to the z. The derivative of e to the minus z is minus e to the minus z. Combining this, we can immediately obtain the result that the derivative of the cosine function, the hyperbolic cosine function of z, is the same as the hyperbolic sine of z, and the derivative of the hyperbolic sine function is the hyperbolic cosine function. So the generalized hyperbolic cosine and sine functions also remain even and odd respectively, right? So hyperbolic cosine of minus z is equal to hyperbolic cosine of z, as can be directly seen just by changing the sign in the original definition, and the hyperbolic sine function of minus z is minus hyperbolic sine of z, so it's an odd function. So the hyperbolic functions are intimately connected to their trigonometric counterparts. So the cosine and sine functions and the hyperbolic cosine and sine functions are very closely related. So we can show this directly from the definition. So cosine of iz, so instead of taking the hyperbolic cosine of z, if we take the hyperbolic cosine of iz, so then we just plug it into the definition, we see that it is e to the iz plus e to the minus iz the whole thing divided by 2, which is nothing but the cosine of z. So we have this result that cosine of iz is nothing but cos of z, and likewise we can show that minus I times the hyperbolic sine of I times z is e to the iz minus e to the minus iz divided by 2i, right? So this comes from plugging in here in this equation and then using, use this minus I to bring this I down here. So then we see that this is nothing but the definition for the sine of z, so which is sine of z. We can also show that minus I times sine of iz is minus I times, just plugging in the definition for sine of iz, which is e to the I times iz minus e to the minus I times iz divided by 2i. But these I squareds will give you minus, and so then you have e to the plus z and e to the minus z, the whole thing divided by 2. There's a cancellation of this I, and you take care of all the signs correctly, and then you'll see that you get exactly hyperbolic sine of z. And once again, it's straightforward to verify that cos of I times z is hyperbolic cosine of z, which can also be seen from this first relation, right? So if hyperbolic cosine of iz is cos z, if you put in place of z, if you put iz, you will get cos of iz is I square cosine of I squared z, but then there is this evenness property of hyperbolic cosine, so immediately you can verify that cos of iz is the same as hyperbolic cos of z. So in some sense you would see that from these relations, cosine of x has this hyperbolic cosine and sine of x along the real axis will behave somewhat like hyperbolic cosines and hyperbolic sines do along the imaginary axis. So in some sense, and vice versa, right? So the manner in which hyperbolic sines and cosines behave along the real axis is going to be similar to how trigonometric functions, they behave along the imaginary axis. So we'll look at this aspect a little more carefully ahead. So let's first look at some identities. One is this generalization of the standard identity involving cosine squared and sine squared. So if we compute cosine squared of z minus hyperbolic sine squared of z, and then we make use of these relations of cosine of z and hyperbolic sine of z. So we have cos squared of iz minus I times sine of iz the whole square. So I'm using this identity here, and so then minus I squared becomes minus 1, and so this becomes, and in place of so I have cos squared of iz plus sine squared of iz, and we have seen that this must be equal to 1 no matter what z is. So this is a generalized result. It holds true for any complex number, and therefore we have the result that hyperbolic cosine squared of a complex number minus hyperbolic sine squared of the same complex number must be equal to 1, right? So in general, this is a useful trick if you want to derive any identities pertaining to hyperbolic cosine and hyperbolic sine functions. Just convert it to the corresponding sine and cosine function using these identities, and then you can use their properties to work this out, right? So we can show that hyperbolic sine of z1 plus z2 is equal to sine hyperbolic of z1 times cos hyperbolic of z2 plus cos hyperbolic of z1 times cos sine hyperbolic of z2. Okay, so using an approach similar to the above or directly from first principles, using the definition of hyperbolic sine and hyperbolic cos, we can show that the hyperbolic sine of z1 plus z2 is the same as sine hyperbolic of z1 times cos hyperbolic of z2 plus cos hyperbolic function of z1 times sine hyperbolic function of z2, and a similar identity involving the hyperbolic cosine of z1 plus z2. Right? So this is something which follows directly from the definition, right? Which you can check explicitly. Now, if you use these relations, and in place of z1 and z2, we just put z is equal to x plus iy, then we have sine of x plus iy, which is just z, is equal to sine hyperbolic of x times cos hyperbolic of I times y, but which is the same as cos of y, and then we have cos hyperbolic of x times sine hyperbolic function of I times y, which brings out this I, and then you have sine of y. And likewise, we can show that cosine hyperbolic of z is cos hyperbolic of x times cos y plus I times sine hyperbolic of x times sine of y. Now, but these are actually nothing but expressions for which spell out the real part and imaginary part of these complex numbers, sine hyperbolic of z and cosine hyperbolic of z, right? So these are useful identities, and it also allows us to work out the modulus squares of these complex numbers. So if we use a line of argument which is very similar to what we did when we were working with sines and cosines modulus squared, right? So in some sense you'll see that it's really the role of x and y get reversed, right? When we're working with cosines and when you're working with hyperbolic cosines, eventually you get mod of cos squared of z is equal to sine hyperbolic squared of x plus cos squared of y. You can check this, and we also have the result mod of sine hyperbolic of z the whole square is equal to sine hyperbolic squared of x plus sine squared y. So, and indeed, these functions are unbounded, as we are anyway familiar with. Even for real variables, it's only real variables which makes it actually unbounded. If you stick to the imaginary line, if you put x equal to 0, then in fact these functions become very they become like the trigonometric functions, like we were saying earlier, and so in fact they will be bounded if your complex number that you're considering is purely imaginary. But so in general, of course, neither of these functions is bounded, but it's useful to have this kind of an identity for the value of the modulus squared. So these functions are also periodic, and their periodicity is it's their period is 2 pi I. So we have seen how sine hyperbolic, we can think of it as really a kind of sinusoidal function, but whatever was happening along the x-axis is going to happen along the y-axis and vice versa. And so instead of 2 pi, so you have a period which is 2 pi I. So sine hyperbolic of z plus 2 pi I is equal to sine hyperbolic of z, which is something you can verify directly from first principles from the definition. Again, cos hyperbolic of z plus 2 pi I is equal to cos hyperbolic of function of z. And so now the zeros of these functions lie along the imaginary axis along. And nowhere else in the plane can you find any other zeros for these two functions. So the only zeros are located at z equal to n pi I for sine hyperbolic of z, and the only zeros for cosine hyperbolic of z are located at these points z is equal to n pi plus pi by 2 the whole times I, again along the imaginary axis. So once again, this is a result which would follow directly from the relationship between sine hyperbolic of z and sine of iz, and again cosine hyperbolic of z and cosine of iz. Right? So we can exploit that to work out the zeros of these functions. Right? That's one way. There are other ways as well. Okay, so we can also define these allied hyperbolic functions. Tan hyperbolic of z is just sine hyperbolic of z divided by cosine hyperbolic of z. Cot hyperbolic of z is cos of z divided by sinh of z. Secant hyperbolic of z is 1 over cosine hyperbolic of z. Cosecant hyperbolic of z is 1 over sine hyperbolic of z. So analogous to how these kinds of functions worked with trigonometric functions, these functions as well here are all analytic at all points except where the denominators have zeros. So whenever cos hyperbolic of z has a zero, so namely points like here, z is equal to n pi plus pi by 2 times I along the imaginary axis, these functions tan h of z and secant h of z, both of these functions are analytic at every point except at these points. And again, cot hyperbolic and cosecant hyperbolic of z have singularities at these points. Z is equal to n pi I all along the imaginary axis. Everywhere else, these functions are also analytic, and wherever they are analytic, their derivatives are also readily written down. Derivative of tan hyperbolic of z is secant hyperbolic squared of z. D by dz of cot hyperbolic of z is minus cosecant hyperbolic squared of z. D by dz secant hyperbolic of z is minus secant hyperbolic of z times tan hyperbolic of z. D by dz of cosecant hyperbolic of z is minus cosecant hyperbolic of z times cot hyperbolic of z. Right? All of these expressions are ready generalizations of analogous results we have seen when we restrict z to be a real number. Okay, so that's all for this lecture. We have looked at hyperbolic functions and the generalization to complex variables in this lecture. Thank you.